Go.
Hello everybody, this is our dress rehearsal demonstration for our National Chemistry Week program for 2025. This is the Cleveland section's main effort for National Chemistry Week, which is the third week of October every year. Before we start, I'd like to introduce the members of our planning committee who have been with us all, spring and summer, getting everything ready. And I'll start with Eve Crane, Katie Arendt, Helen Mayer, Joe Yurko, Valerie Condon, and Shelly Yang. And I'm Bob Fowler. Okay, stop for a minute, Mark, and we're going to...
One.
Okay, continuing with the program, if you'll pardon me, I've actually got some notes that I put together that are kind of germane to this year's program. I don't want to miss anything, so I'm going to refer to these as I go through it. First of all, the theme for this year's program is the hidden life of spices. But of course, we decided early on, our planning committee did, that we were not going to allow any tasting or eating of any of the spices that are involved in the program. It's just not appropriate to do so. So that kind of limited what we could do with the spice program this year. Some of the spices that we're going to use, in particular turmeric, are really messy. So what we'd like for the demonstrators, for you guys to do, is as soon as the kids come into the program, have each one of them don an apron and their mask. We have gloves for them later on when they get to the turmeric experiment, but they don't need to don their gloves just yet. The demonstrators, you guys don't need to purchase anything special this year, but there is a list of items that you need to bring from home on page 7 of this year's script. I haven't got it open to the cover, but this year's script, there's a copy of the script in each one of your kits. And just a couple more things. Make sure you call the children's librarian at the library that you're going to have your demonstration at least a week or so in advance, for a couple of reasons. Number one, to make sure that they've got the room set up appropriately, which means 5 tables with 5 students each for a maximum of 25 students, to make sure that, if possible, they can provide an assistant for you. A lot of times the libraries will have interns that are available, and if you give them enough warning, enough notice, they can have an intern available to help you. And I think this year, having an assistant will be extremely helpful. The other thing that I think you need to ask the librarian, please, can I get into the room an hour before the program is scheduled to start? That's so you can get things set up. And tell the librarian that you're also going to need at least a half an hour after the scheduled finish of the program to make sure that you can get everything cleaned up and put away. This year, there are 4 experiments, but a couple of the experiments, namely experiment number 1 and experiment number 3, have 2 different parts. So in reality, there are 6 experiments. Note that there's a list of items on page 26 of the script that the students can take home with them this year. And speaking of finishing up the program and taking home things, we would like for you to note that on page 27 of the script, there's some new information, a different way of returning items back to me, actually through the interlibrary loan. Because we have so many different items this year, we're going to demonstrate one of them in just a minute. Katie's going to demonstrate a balloon pump. And since we have so many things to return, we'd like for you to put things back into your kit box, which hopefully is empty by now. Put a label on top of the kit box, and it's in your kit. I think Mark put the labels with the script, I believe. It says, return to Julia Boxer. Julia is our contact at the CCPL, the Cuyahoga County Public Library, and everything goes to her, and then when she collects everything, she gives me a call, and I go down and pick them up and put them back into our lovely storage bin. And Eve, one of these years, I'm going to take you over to that storage bin and introduce you. It's a wonderful place. Okay, with that, I'd like to start the program, and Katie, if you would come up and demonstrate something that needs to be done by the demonstrators in advance of the program. We have a balloon pump, because we need balloons, and there's going to be 25 of these balloons. You actually got it to work, huh?
Yep. Works properly now.
What's going on? Is that big enough, you think? Okay.
Yeah.
All right.
I don't think they would be huge.
Yeah, they don't need to be huge. What we're going to do is we're going to use the balloons to generate some static electricity. As soon as Katie gets it tied off, we will. Good. Thank you, ma'am. Okay. Hopefully, you'll be able to blow up and tie off 25 balloons before the program starts. There are 2 large trash bags in your kit, one for the trash at the end of the program, and the other one for storing these things in. Once you get them blown up, if you give them to the kids, you know the racket and the nonsense that's going to create. So what we thought is just put the 25 balloons in one of the trash bags, then have that assistant we talked about actually have them pass them out as we get to experiment number 2 or 3, whatever it is, that uses the balloon and uses static electricity properties. Okay, let us start. It's actually experiment number 1. Let's start with experiment number 1, and there's 2 different parts to this experiment. The experiment is about the spice called pepper, the king of spices. It's called the king of spices because in the old days along the Spice Road, Silk Road, Spice Road?
Silk Road.
Silk Road, okay. Spices used to come from far away, India, places like that. And they brought them back to Europe. Spices got pretty expensive, and they actually were used as currency for a while in some places. So one of the most famous and very useful spices is pepper, in particular black pepper. So we're going to talk about some black pepper right now. What we're going to do first of all is we're going to take the bowl. No, that's the other one. Excuse me for 1 second. We're going to start with jumping pepper. On this little paper plate, ask the students, and each student will have a little paper plate like this, and they'll have 2 packets of pepper and 1 packet of salt. Ask them to take their 1 packet of salt, open it up, and sprinkle it as evenly as possible over the paper plate. And the first packet of pepper, have them take it and sprinkle it over the top evenly, sprinkled over the top of the salt. Then when everything is on, the salt and the pepper are both on the tray, have them move it around just a little bit, and now tell the kids, okay, I would like to find out if there's some easy way to separate the pepper from the salt. Okay, students, all you kids out there, anybody have any good ideas for how we can separate the pepper from the salt other than going out and picking them out one by one? Okay, students, what would you suggest we use for separating the pepper from the salt? Student Katie over there almost had her hand up. Well, what we're going to do, demonstrators, is we're going to have the kids take the balloon. And at this point, have your assistant pass out the balloons, and then ask the kids, I think we need a student. Katie? Ask the students to rub the balloon fairly well on their hair, generate some static electricity, and then pass it. Oops, you didn't do enough.
There we go.
We got pepper jumping onto the balloon, right?
Mm-hmm.
Okay, that's called the jumping pepper experiment. Like I said, we don't have a lot of chemistry involved this year, simply because we can't do much with the spices, we can't taste them, and we can't have the kids eat them. Now, what happened? Why did the pepper jump onto the balloon? Students, any idea? It's called static electricity. When you rub the balloon on your hair, you actually imparted electrons from your hair onto the from your hair onto the balloon, and when you pass the balloon over the salt and pepper mixture, the more static electricity, by the way, the better. So have them rub their hair pretty well. What happened was that the electrons, the negative electrons on the balloon, actually polarized the little flakes of pepper. And since the pepper is very light, and you have a polarized situation, you have negative and positive attracting each other, and we can tell the students that the pepper flakes actually jumped onto the balloon, and that's how we separated the salt from the pepper. Okay, now, we've got one more thing we'd like to do as part of experiment number 1. The students have a second pepper packet, and have them shake it like that to get the pepper down to the bottom a little bit, tear off the top, and then distribute the pepper around the surface of the water fairly evenly. And tell the kids, where is pepper? Well, pepper's sitting on the surface of the water. Why doesn't it sink? Well, it doesn't sink for 2 reasons. Because water has something called surface tension, which is like a skin on the surface of the water. Surface tension, the skin on the water, is why when water falls as rain, it falls as drops and not as sheets, because that surface tension makes the drops cling together as if they had a skin around them. Well, that's part of the reason why the pepper is floating right now. The other part is that the pepper is very, very light, so it doesn't sink. Let's try something. I have here, in each of the tables for the 5 students, each 5 students will have a 10 ml vial like this with just regular dish detergent in it. And what we're going to do is we're going to have the students one by one pass this around. They each one have a Q-tip. Just have them dip the Q-tip into the detergent and put it right in the middle of the bowl, and then pass the vial on to the next student and have each of the students repeat the process and have them look at the bowl. What happened? Well, the pepper all moved to the side of the bowl. Why is that? Well, because when we added a detergent, it's called a surface active agent, a surfactant for short. Your mom uses detergents when she's washing the dishes. Why? Why is detergent, why so important when washing the dishes? Well, detergents, being surface active agents, destroy the skin on the surface. They destroy the water's surface tension, and they make the water wetter. So washing dishes is easier once the detergent is added, among other reasons. And why did the pepper flakes all move over to the side of the bowl, which is what happened? Well, when we put the detergent at the center of each bowl, into the water at the center of each bowl, the surface tension was destroyed by the detergent, just like it does in Mom's sink when she's washing her dishes. And the water molecules are still attracted to each other. They all pull away from the center, and they carry the pepper along with it. Okay? That is experiment number 1. Yeah, why don't you pause, Mark, and we'll have...
Okay, so the experiment 2 is cinnamon bubbles. And to do this experiment, the kids are going to want to find another bowl of water, hopefully intact. And then, is this enough cinnamon here? Is this enough cinnamon? I guess
yes, it is. It's a tablespoon.
It's a tablespoon. Okay, cool. All right. So they'll have the cinnamon here, which what you want to do is make basically an even layer of cinnamon, just kind of dusting the top layer of the water. And then we're going to put bubbles coming up underneath that, and then you can kind of roll these bubbles around. Basically, it's just water. So there's no soap actually making the bubble. It's just a bubble made of water and cinnamon. And so the interesting thing about it is that the cinnamon, the actual kind of more of a macromolecular structure of the cinnamon, it'll form kind of interlocking things, and so they'll dry, and you can make these cinnamon bubbles. And theoretically, this will be fine. Now, what happens is the cinnamon will start sinking into the water, and then it's hard to do it anymore. And so, if there's some extra cinnamon packets that you have in case the kids end up dumping all the cinnamon in at once, for example, that's not going to be good. If you want to have them use a spoon and sort of gently distribute it over the surface. I don't think there's going to be enough cinnamon. Maybe it's my bad in my calculation. This is probably not going to be enough for the size of the bowl, honestly.
Oh.
We're going to need like way more cinnamon. Like a lot
Got
more.
a lot more cinnamon.
We might need a lot more cinnamon.
Stop.
Okay.
Hold on. Starting again.
Starting again. Okay. So forget what I said about there not being enough cinnamon. But anyway, so you definitely want to have the surface covered though, and then basically you use this little syringe, which is, if anybody had their molars out, is kind of a dental syringe, which we thought might be nice because it'd be harder to poke your eye out with it. But essentially it's curved, so you want to dunk it under that cinnamon layer, and then just very gently, make bubbles under that. And so then, using these ice cream tasting spoons, just because the bubbles are very fragile, and if you use a larger spoon, it doesn't quite work as well. You can actually nudge them around on the surface and coat them sort of like a little snowball, but you don't really accumulate that much cinnamon on it. Oh yeah, you gotta get in here too. So yeah, these little balls are actually rolling around. And so each student probably will want to have a couple of these spoons at least so they can kind of manipulate it. But then you can put it on the spoon kind of but they will pop like a bubble. It's kind of two stuck together. But yeah, so this is basically how it will work. They could theoretically bring these home with them. They're a little bit fragile. But yeah, these bubbles are very stable. And so people make them for like pastries and things like that you could use for, I don't know, there's various things you could potentially use it for. I'm not sure if it really has a definite function, but they're definitely fun, I think, and it's a little bit, it may take them a few tries to kind of get it right, and there is extra cinnamon in case all the cinnamon sinks or someone did something bad with it. But
there's an extra little baggie if they want
they're
to take
pretty
it
fun.
home.
Yeah, the baggie to take them home.
Can you roll them around, Eve?
Certainly on the surface of the cinnamon you can. They pop. Some of them do pop. But anyway,
You have to be very careful.
Well, yeah, if you drop it, it will pop. But they will become, once they harden, and maybe it's something you can do at home with additional cinnamon, because it's literally just cinnamon and water. That you can do it at home and play with it that way. And probably, then allow them. But once they're dry, which probably may take, overnight or something like that, then they'll be stable.
Eve, there's a little extra plastic bag for the kids to take home their cinnamon bubbles if they're still intact.
If they're still intact, they
If
can
they want
try.
to.
Because I know they do like to take stuff home. So anyway, so that hopefully they will find somewhat entertaining and not too frustrating. You can also potentially use a larger spoon as well, like there you got one in. So that is that experiment. But it supposedly will work with other spices, for example, dry mustard and some other materials will also kind of stabilize the bubble from that structure.
Okay.
They just don't smell as nice, right?
They don't smell as nice.
1.
Okay, so experiment 3 has 2 parts, and it also, obviously experiment 2 kind of made a mess, but experiment 3 makes a more sustainable mess. And so both of these have to do with turmeric, and turmeric can be used as a natural dye, or, an accidental dye, I suppose. So you do, and it will stain your hands and clothes, and can be very difficult to remove. So basically what you want to do is encourage the children to use, or the students, to use their aprons. They're going to have gloves that they'll wear specifically for this, and then you can collect them afterwards because they're all going to probably touch their face after they get the turmeric on it. Okay.
Eve, you might want to mention that what we did before was an individual.
Yes.
And what you're doing now is a group, is a demo.
Yeah, so the cinnamon experiment is done at each table so that each student will be able to kind of interact we'll have one bowl per table, so probably they'll need to take
Two bowls.
Oh, 2 bowls per table. Oh, 2 bowls per table. So that'll be good. So each student will be able to kind of get in on the action. This one, the first part with the isopropanol is done because we have a wine glass, and the isopropanol is probably not great to have all over the place, and the black lights are all over the place. That's going to be just a demonstration. So the first part is to find the black light.
That's what I'm looking for. Where'd it go?
But
You got one?
is it still lit? So basically,
I think you might have stopped it. Did you stop it, Mark?
Oh, keep going.
Go.
Yeah, so the first part is isopropanol. Now, we have isopropanol that's in various containers. It's wrapped in bubble wrap in your boxes. So it does say ISO on it. In a panic, don't drink it. Anyway.
Spoke like a true physician.
Anyway, it'll be all right. Because it's not going to be distributed to the kids. And don't drink the vinegar either, but okay. So, yeah. So turmeric has a lot of interesting properties. You're at risk of having all of the experiments taken over by turmeric, I think, because of its interest. But so essentially, turmeric will form 2 slightly different forms when it's in an organic compound versus when it's in water. And what we find, I don't know if we can maybe try it without with the lights on, but it'll actually fluoresce under UV light when it's in isopropanol, when it's in an organic solvent.
There you go.
Okay. And so for this, you really want to add a very dainty amount because it kind of looks cool. Well, it should. I shouldn't say until we see. But if you add a whole bunch of it, which I can at the end, you don't kind of see the trailing on here. But it's kind of cool. Woo. Yeah, so you want to just be kind of dainty to see it kind of going in there. Now, you could be smart in the end and get
now I see it. Now I see it.
Oh, you can see it better. Yeah, so we may want to have this elevated or have it set up so you can.
This is where you need your assistant to
Yes,
hold
your
it.
assistant.
In the text, it says, have your assistant hold the light for you.
Okay.
Or a parent or somebody that may be around.
No,
You're only doing, one of them. Yeah, so this is, so it works pretty well.
That has a high wow factor, right, Katie?
Yep. I hope so.
Yeah, that's cool.
So that's pretty cool. So you can see you really don't need very much. And what you can do, you can either have a second glass or you can add and show it really doesn't do that in water. In water it doesn't fluoresce like that. So it's kind of a special feature of it being an organic solvent.
Well, it's not soluble in water, is it?
It quenches in water.
It just quenches. I mean, I don't know if it's necessarily even dissolving.
It's non-solubility effect.
Yeah, it's just,
Oh.
Which is kind of how the form of the actual curcumin is in the isopropanol, but I'll look forward to the write-up. Yeah, the write-up has it has the images of the molecules, which is nice. Okay, so that is the first part of the experiment, and that's a demonstration. The second part is going to be the actual at each table. And so in this part, turmeric, in addition to being a dye, it kind of has a slightly different color depending on the pH. It's not very good for pH in acidic conditions. It's always pretty much yellow. But under basic conditions, it will turn kind of more red to kind of a dark red brown. So to do this experiment, what you're going to want to do, you've got kind of different, you have like a tablespoon of water in each of these cups. A for acid, B is for our baking soda, then we've got water, and we've got washing soda. So baking soda is sodium bicarbonate, so we're going to kind of put these in a different order here.
Eve, the first cup marked A has vinegar in it.
Yes. Oh,
Okay,
good.
the rest
Sorry.
of the 3 have water.
Oh, yeah. So this one has vinegar in it. This shows a tablespoon of vinegar. Sorry. So this is A for acid, which is our vinegar here. Then you also have another cup here that's marked B, and that's just more vinegar. Can't have enough vinegar. And then you've got another cup here that's marked water, just so that you can basically dispense the water amongst the cups. Now what we're going to do is we're going to dissolve our baking soda, B, and it should be 1/4 teaspoon. The exact amount really doesn't matter, but basically pouring that into the cup marked B. You can swirl it to dissolve. Maybe that's not good to recommend. You can stir it to dissolve it. That might be safer. It may not all dissolve, which is actually okay too. Hopefully it don't splash around everywhere, but they're going to be wearing goggles. Real goggles. Okay. Now, this is, so washing soda is sodium carbonate. It's much more basic. I would encourage this to be added by maybe one of the older students. It's not really something to completely mess with. So this is not something that they should touch their face or anything else with. And this well, it's not going to dissolve very well. You also don't want to splash this, really. Okay. So now we've got an acid, we've got plain water, we've got a weak base with our sodium bicarbonate, and we've got a stronger base with our washing soda that's sodium carbonate. So to introduce the concept of pH, and we're gonna have multiple of these things that they'll have to kind of see how pH works. And we'll also have, don't we have our pH paper? Mm-hmm. Oh, we do. They'll also have pH paper. So you want to, beforehand, have one of these strips, one of these packages with you in each kit to give 5 or 6 strips to each, at least 5, but probably more, so they can play with it a little bit more to each taste. And then they can test basically each one and then compare it with the pH paper. So let's see if hopefully it works. We have acid. Woo! It's pink. Okay. We have regular water. Still okay here in Cleveland? It's okay. Now we've got our weak base. Ooh, it's blue. And a strong base. Ooh.
Oh, yeah.
Yeah, so this is a real strong base. It's good for your laundry. A little tidy whitey white with that. Okay, now, so those are all, so we can see how a pH, kind of a pH indicator would work, because we've got this pH paper that somebody spent time optimizing. But can we just use a spice instead as a pH indicator? And this is some turmeric. I hope I'm using the correct containers. Again, it doesn't have to be exact, but we add about 1 teaspoon or ½ teaspoonful, some amount, basically 1/4 of it to each one. There's our acid. There's our water. There's our baking soda. And there's our washing soda's fun. Okay. So now you can see already that this washing soda has gotten really dark in here.
Yeah.
And I'll actually put it on a paper towel so that we can see it a little bit better. And the acid, and so kind of you can buy different types of pH paper. Some are more sensitive in certain ranges than others. And you can see if you bought a turmeric-based pH paper, it's not going to work too well between differentiating acid and water. It's basically the same yellow color. But as we get here to the sodium carbonate, sodium bicarbonate, your baking soda for your brownies, this actually is a little bit darker. We can see it's starting to turn kind of orange.
Right.
Yeah, more of a kind of orangey red as opposed to just yellow. But once we get to the washing soda, it's really deep red. So certainly you want to make sure that no one's contaminated your food with something basic. You can dump in some turmeric and feel assured. Alright, so now what is, so now we have the chocolate, kind of fun. With the remaining vinegar, what you can do is actually add some of it to kind of show, or you may want to come back, sorry, well maybe not, maybe we'll see if it works. So vinegar is acetic acid, and then we can add it into this. Well, it's sort of working. I think it works better in the it works the best in the baking soda. is you get, you kind of can change it back. Once you drop the pH, it goes back to being bright yellow, and then you also get carbon dioxide released. When you do that, it's not as exciting. It's working.
Oh,
It's
yeah.
There it goes.
working.
Yeah, it's going.
Okay.
That'll get a wow factor too, right, Katie?
Something to do. Yeah, so you're kind of neutralizing that base with the vinegar. Now the vinegar is a pretty weak acid. Well, particularly this vinegar that we got. But no, I think it's probably standard vinegar. So yeah, so it's kind of fun. You can change it back to yellow, but then you can see kind of once there's more of the washing soda that comes in and reacts to it, it goes back to red. But you kind of have a slightly different color. It's probably could be a slightly different pH, and if you wanted to, you could actually test the pH again to see what you did to it, and see if it's a little bit less than the first one. And it looks like it is, yeah, it's a little bit less. I mean, it's a little bit messed up because you have the color on there, but you can see, yeah, I have dropped the pH by adding the vinegar. But that's probably about it. What you don't want to do, which I did do at home, I don't know why I did it, you can dump the vinegar in there and make a volcano. I was like, oh man, but
Probably not a good idea.
it's not just a volcano, it's a turmeric volcano that stains everything in its path. It's just one of those things, which hopefully no one will do. Or you should do outside.
You gonna add vinegar the first 2 cups each?
Oh yeah, so this is water. So vinegar and water, basically the vinegar's already diluted acetic acid in water, and this already was vinegar. So it's just more vinegar. But then you don't want to do it. Okay, don't do that. It's okay. Yeah. It's cool spread. So I don't know, and hopefully that's entertaining for them. Oh yeah, so what you don't want to do is touch your face with that stuff. Yeah, so we have the trash bag is in part and a bucket, most likely, to collect all this liquid waste and get that out of the way before the last.
Yeah, at this point, I think it'd be a good idea for the assistant to come around and take these things, dump the liquids into the bucket, and throw the cups into the trash bag. And get rid of that stuff.
Yeah.
So then the kids can't use it to stain anything. Remember, that's just...
1.
Hi, my name is Joe Yurko, and we're going to do experiment number 4. And that's going to be newly minted Play-Doh. And in this experiment, we're going to test spice to see if spearmint extract oil containing a chemical with a strong mint smell will attract pollinators and repel herbivores in your home garden. We will prepare a minted Play-Doh to take home to test in your flower garden. So, make sure that you keep your gloves and safety glasses on from the previous experiment. Locate your bag for experiment number 4, and we'll take the white styrofoam bowl and we'll add the salt. It's a pink salt. I don't know why it's pink, but we got pink salt. Fancy home beverages. And then before you start, you'll heat up a half cup of water in a microwave, and you'll have a measuring cup, styrofoam cup, and it has a half cup marking in it. So you'll fill that up to the half cup mark, and then you'll add that to the salt, and then you'll have about 2 minutes of this to work with this. And in that time, you'll read the next statement while you're stirring, or your coworker will read. And Valerie, will you read this?
Mint leaves are made up of small cells, like a building wall is made up of small bricks. In the mint cells, they have small parts called organelles that keep the cell alive and growing to replace other cells when they die. Mint leaf cells also contain glandular trichomes that release chemicals called terpenes when the cells are damaged. This occurs to protect the mint leaf by repelling herbivores, which are plant-eating animals and insects, that will want to eat the plant. The terpenes also attract pollinators, like butterflies and bees, to help generate more mint plants. The terpene chemicals secreted from the glandular trichomes have a strong mint aroma that you should be able to smell. The spearmint extract oil we are using today is made from mint leaves.
And we're about 45 seconds away from finishing the stirring. And you also have a bag containing pipettes. And there's 4 pipettes, not 3. We needed 2 pipettes of the oil, so we added that to it. And then we're going to open that up once we're done stirring. And from home, you need to bring some scissors, and demonstrator will cut the tips off of the pipettes and squirt those into the mixture while stirring.
You need about 3 hands for that, Joe.
Yeah.
We have several children.
I'll give my right arm to
Yes.
have 3 hands.
It's very, very small.
Yeah,
Yeah,
we
this
can start
is-
cutting for you.
Sure. Okay, that's the time.
Start.
Yeah.
Okay, they've been sealed on the end, so we're going to cut the tops off on them. Each one is labeled, and you can tell them what it is.
Yeah, this is the juice that's going in. You might have to pinch it a couple times, point it down, handle it by the stem, and gently grab the bulb. And then when you're ready, you can start squeezing the bulb in. And this is the mint flavor, so we did the juice first, the mint, and then this is the oil. And then we're going to mix that in. And then we got this one. This is the second mint, or the second oil. So we do a juice, a mint, and an oil. Then you just stir that for a couple seconds. And then you're ready to move on. You can ask the students if they can smell the mint aroma. Ask them if they know what plant pollinators are. And pollinators are usually butterflies, bees, moths, and that helps the flowering plants reproduce. Then you can ask the students what plant herbivores are, and herbivores are usually deer, caterpillar, grasshoppers, and aphids, and they tend to eat the plant leaves. And we're hoping that this particular mint spearmint will repel them from eating and attract the pollinators. So next we're going to add the flour, and that's this other bag you have, and it's the larger white one. And you sort of add that gradually as you're stirring. So you can add that, and this is where it should start turning into a dough. We're lucky.
Now he's got her fingers crossed.
So you gotta get that all mixed up with your mixing fork. This is where your apron will help out. And usually a couple students can work with this. One can hold the bowl or move the bowl around, while the other students tend to they can share with the mixing if one gets tired and mix it. There'll be some lumps settling up. You want to make sure your fork breaks a lot of those lumps down that are in there, and this will give you a good consistency. And the thicker it is, the better. In the event that it's too thin, you may need to take it home and add more flour to thicken it up. But there's a take-home bag, and there's 5 bags per table, and inside that bag you have a string so that once it's done you can roll it out into a log and break that up into 5 parts and roll those up into logs. Then you can press the string in the center of that log and then roll it some more. Then you can put that log in this bag, and along with that is a set of instructions from American Chemical Society, and that tells you the recipe to make this. And then you can, put your Play-Doh, which is
Needs more flour.
needs more flour, so you can take that home.
Should we
And-
ask people to bring
Bring
a little
more
extra flour?
Yes.
I mean, most people probably have some flour and you can just add
Yeah.
some. That's probably the best way of doing it.
Yeah,
Because you don't know if you're gonna get the right amount of water.
Yeah.
so you'll have that to take home. And the chemicals that are in the glandular trichomes are your terpenes, and those are either to defend the plant or attract animals or insects. So one of the terpenes is carbone and the other is limonene, and carbone is a monoterpenoid ketone, and the limonene is a monocyclic monoterpene. So the carbone is the most abundant chemical in the spearmint oil we're using today. So thank you, and hope everything turns out, and enjoy your experiment.
2, 1.
Oh my gosh, you're gonna.
Thank you to all of your demonstrators out there. We really appreciate your help in carrying on our program to the kids of this county. And just wanted to comment, Joe told me that if everyone would bring a little bit, that's not wine by the way, everyone would bring a little bit extra flour with them so that the stuff has a consistency of not Play-Doh, but pizza dough at the end. They should be able to roll it into a ball and roll it around a little bit, right?
Yeah, just like bread dough.
Just like bread dough, and take it home with them. Okay, thanks again for putting on the program. We really appreciate it. Take care.